In this project, we will numerically validate the data obtained by the paper named Numerical Model and Effectiveness Correlation for a Run-Round Heat Recovery System with Combined Counter and Cross-Flow Exchangers. As you can see in this slide, we have extracted the figure 2 of the paper, which shows a schematic of a flat plate counter cross-flow heat exchanger. The 3D geometry of the present model is designed by Design Modeler software. The meshing process of the present model is performed by ANSYS meshing software. The mesh is unstructured and the element number is equal to 155,000. In this slide, you can see that we have extracted the figure 11 of the paper, which shows the thickness of the heat exchanger over the entrance ratio. Now we're going to use the data provided in this graph to validate our CFD simulation project. Also, by clicking on Report Quality, again in the Console tab, the Fluent software will give you the quality report for your mesh. For example, you can see the maximum aspect ratio of your mesh, maximum orthogonal quality, and etc. In the Appear window, which is for example for the density, you can see that this property is defined in terms of temperature with a polynomial function with 3 coefficients. These coefficients are listed below. Also, you can plot this function by defining the direct variable and its min and max value. Also, you can define a new material just by clicking on New button, and in the Appear window, just like before, just have to click for the polynomial function and then click on Edit in order to define your coefficient. By clicking on the outlet air boundary, you will see that the type of this boundary is defined to be pressure outlet. By clicking on Edit, you will be able to change the settings for this boundary. As for the wall boundaries, by clicking on Edit, a new window will appear. Under the Momentum section, you will see that the wall motion and shear condition for this boundary is set to be stationary wall and no slip. By clicking on Thermal, you will see that the heat flux thermal condition is defined for this boundary, and the value of the heat flux is set to be 0, which means that this wall is adiabatic. As for other walls, the similar settings are applied to each of them, and since it was mentioned in the first slides and in the project description slides, the wall are insulated, the thermal condition defined for each of these boundaries are heat flux, and the value of the heat flux is set to be 0. After double-clicking on the Residuals button, a new window will appear. In the Appear window, you can see the absolute criteria for equations like continuity, x velocity, y velocity, and so on. Now, when you set the software to start the simulation, there would be error between each iteration. Now, if that error is less than these criterion, it conveys the meaning that that equation has reached convergence. After clicking on location and then selecting plane, a new window will appear. In the Appear window, under the definition section in front of the method, we click on ZX plane and then set the value of y to the defined value. And then we apply to create a new plane. In the shown contour, which is for the pressure contour, you can easily see how the pressure of the liquid changes from the inlet section to the outlet. As was explained before, in the variable section, you can change the variable from pressure, for example, to the temperature, and then apply, and you will be able to see the temperature contour. As shown in the temperature contour, you can easily see how the temperature of the liquid has decreased from the inlet section to the outlet. As was mentioned in the project description slide, you can easily see the inlet and outlet of the liquid in this streamline contour. Also, we need to calculate the outlet temperatures of air and the liquid for our calculations. To do that, just like the previous slide, we right-click on the surface integrals and then select Edit. To calculate the values for total heat transfer rate and outlet temperatures of airflow and liquid flow, we implement those values in the existing formula as you can see here, and then calculate the effectiveness of the heat exchanger. Finally, the summary of different settings and setup that we have used in our project is presented to you in the slide.
Obtain the mesh file and also the full training movie by purchasing this product.
As you can see in this slide, we have extracted the figure 2 of the paper, which shows a schematic of a flat plate counter cross-flow heat exchanger. This heat exchanger consists of two special flow channels. The airflow flows from one side of the central panel, and the flow of solution flows from the other side but in the opposite direction to the airflow. In general, this panel belongs to one of the two panels in the closed cycle of solution and airflow. The fluids used in the present model include air and ethylene glycol, although their thermophysical properties are manually defined in the Fluent. Ethylene glycol is a colorless, odorless, low volatility, low viscosity material whose properties are defined as temperature-dependent polynomials. Also, since hot and cold flows are not integrated in this heat exchanger, there is no need to use a multi-phase flow module, and on the other hand, a separating plate is used as an interface. The dissolved fluid in the model has a temperature higher than the airflow temperature, and therefore the purpose of the problem is to cool the hot airflow outlet. The general purpose of the present problem is to study the fluid behavior and heat transfer of the flows and to investigate the performance efficiency of heat exchanger. In this slide, you can see that we have extracted the figure 11 of the paper, which shows the thickness of the heat exchanger over the entrance ratio. Now we're going to use the data provided in this graph to validate our CFD simulation project. The 3D geometry of the present model is designed by Design Modeler software. The present model is a heat exchanger panel with two flow paths, such that on the one hand, the hot liquid flow and on the other hand, cool air flow in the opposite direction to the liquid flow. The outer wall also act as insulators. The meshing process of the present model is performed by ANSYS meshing software. The mesh is unstructured and the element number is equal to 155,000. The cells are smaller and more accurate near the wall boundaries. To benefit from Master CFD services including simulation, consultation, and training, contact our experts via info@mastercfd.com.